Hi Year 12. This lesson we are going to consider reaction profile diagrams on page 135. Now if you think back to your rates of reaction topic, we learned that chemical reactions can only happen when particles collide. Now the particles have got to collide in a certain way and they've got to have the minimum amount of energy if these collisions are going to be successful and they're going to go on and cause a chemical reaction. Now this minimum amount of energy that we talked about is called the activation energy. And the first thing that we're going to do is remind ourselves with each other that definition. So we're going to write in that the activation energy is the minimum amount of energy required for a reaction to happen. It's the minimum amount of energy that the collision must have. Now, if we look at the first example of one of these reaction profile diagrams, you'll notice that we have got energy on the y-axis, and along the bottom then on the x-axis, we've got the progress of the reaction. Now we're looking at the energy level of the reactants and the products. In this example, the energy level of the reactants is greater than that of the products, but we'll talk more about that as the lesson progresses. Now we're looking at the profile for the reaction. So if the reactants start with a certain amount of energy, energy needs to be taken in during the collision for all the bonds in the reactants to be broken. Then the atoms from the reactants rearrange themselves, they form new bonds, and actually when they form new bonds, the energy is given out until they form the products. Now we're interested in the amount of energy that's taken in to break these bonds, and if you look, you can see that the activation energy is labelled there. So it's really the energy, like I've said, that's needed to break the bonds in the reactants. Now you're going to need to be able to draw one of these energy profile diagrams for both an exothermic and an endothermic reaction. But before, we're going to write into your notes that a reaction profile for a chemical reaction shows how the energy of the chemicals change as the reaction proceeds. And remember, you can pause the video as you need to. We're going to go on then to say that the reaction profile is drawn as a graph sketch of energy on the vertical axis against the progress of the reaction from reactants to products on the horizontal axis. Now this is all much easier when we draw. So if we look at the first example then of an exothermic reaction profile, and we're going to draw this into the space. Now the first thing to do is draw your axes and be very sure that you have labelled your axes, as there are marks for this in the exam. So the y-axis is the chemical potential energy, or just energy is fine. The x-axis is the reaction progress. Now we're going to draw a line and we're going to label it the reactants, draw a line and we're going to label it the products. And we're noticing first of all that in an exothermic reaction, the reactants have a higher energy than the products do. Now if we follow the reaction progress then, energy has got to be taken in to break all the bonds in the reactants. The atoms in the reactants rearrange themselves and they form new bonds, and this gives out energy, and they form new bonds to form the products. Now we've already mentioned this activation energy, so what we're concentrating on this lesson is the red arrow. Now the red arrow is pointing down, and you can see that it's labelled up as the heat energy that's released in this exothermic reaction. Now this symbol delta H is just showing you the energy change. Now if you notice that the products have a lower energy than the reactants. So if we were to take away the reactant energy from the product energy, this would give a negative value, and hence exothermic reactions always have a negative value for their energy change. And we mentioned that in a previous lesson, but this is important. Now, if we were to think of it in terms of bonds, and we will do this in more detail in our next lesson, more energy is released by bond forming than is absorbed during bond breaking, So overall energy as heat is released by an exothermic chemical reaction. And it's really important that as you copy in the diagram, you add all the labels. Now moving on, profile diagram for an endothermic reaction. But before we do, we're going to explain this exothermic one at the bottom of the page. So in an exothermic reaction, chemical energy in the reactants is converted into heat energy, which is released. This means the products have a lower energy than the reactants. The change in energy is written as a negative number. So that needs to be copied into your lines just below your diagram on page 135. Now moving on then, so we can consider an endothermic reaction. Now again, draw your axes, take care to label them up, but what we really need to notice is the energy level of the reactants and the energy level of the products. Now it's the opposite way round to the exothermic reaction was. This time the reactants have less energy than the products. The activation energy is labelled up just the way we did in the exothermic reaction. But if we think about these two energy levels, okay, and if we think about it in terms of bonds formed first. So more energy is absorbed by bond breaking than is released during bond forming. So overall energy in the form of heat is absorbed by an endothermic chemical reaction. Now if we think of this delta H, which is just the change in heat energy. This time the products have a higher energy value than the reactants. The energy difference then when we take the reactant energy away from the product energy will always be a positive value. So hence endothermic reactions always have a positive energy change. So take care that you draw in the diagram carefully and you add in all the labels. Now like that, add in an explanation just below. So in an endothermic reaction, heat energy from the surroundings is converted into chemical energy in the products. The products have a higher energy than the reactants, and the change in energy is written as a positive number. Now before we leave these reaction profile diagrams, we are going to consider the effect that a catalyst has on one of them. Now we know from our rates topic that a catalyst speeds up a chemical reaction. We know that it does this and it's not used up in the process, but we are adding a bit onto our knowledge now, and we are going to learn that a catalyst actually speeds up a chemical reaction by providing an alternative pathway with a lower activation energy. Now this reaction profile on the screen is for an exothermic reaction, but we could apply it to an endothermic one as well. Consider the blue pathway for the chemical reaction. So the reactants start with a certain amount of energy. Energy is taken in to break the bonds, the atoms rearrange, and energy is given out as new bonds form to form the products. Now the green arrow is showing you the activation energy, the energy that the reactant particles must have when they collide without the catalyst. Now if we compare that then to the red reaction profile, if we add a catalyst in, well, energy is still taken in to break the bonds in the reactants, and energy is still given out to form new bonds when we're forming the products. But look at the red arrow. This is an alternative pathway. The activation energy is lower, like you can see, and that means that the particles can collide with less energy. The collision will still be successful because of this catalyst, and it will go on then to form the products. So it's really important that we understand how these catalysts actually work.